So welcome back everybody to EE240. Hope everybody had a good week at ISSCC. So now we get to dive back into the real stuff, so to speak. So I did post the next homework up on the web sort of over the last week. How many of you guys have actually taken a look at that already? Okay, good. So I did push the deadline back from the original, so I think it's due basically a week from today. But the following homework will be due essentially like a week and a half after that, so I'll be posting that probably later on this week. So that's not to say that you guys should be slacking, but since we didn't quite get to cover all of the material, I figured it'd be unfair to make you sort of finish everything within sort of 2 days or something like that. So this homework is due next Tuesday, and then the following one will be sort of due, let's say, 2 weeks from this Thursday. So any kind of questions on either material or anything like that?
I was looking at the schedule. I noticed it's
6:30, I think. But
okay,
yeah.
6:30 to 8 p.m. What's up with that?
So usually that's what people prefer. I'm fine with sort of moving it to be during class, but usually people have preferred to do it in the evening, so I guess we can take a quick poll now. So who prefers to do it in the evening? Raise your hand. Okay, well, I guess, Will, that answers your question, huh?
Okay.
Is there somebody who really, really strongly prefers to do it in the morning? Will, you can raise your hand. That's fine. Okay, yeah, so I think we'll stick with the evening, but, you know, come bug me if there's any, like, major issue you can't make it. Obviously, if you really can't make it, then you should let me know, like, now. There's one person who's already told me that, so, you know, if you know that you can't make it, definitely let me know that ahead of time so that we can actually take care of that and make sure everything happens. Any kind of questions on non-logistic stuff or material or anything? Okay, so we'll sort of smoothly ride back into stuff, and I'm sure that maybe that'll... Oh, yeah, question?
Do you have any more copies of the
No, so whatever I handed out is what's there, unfortunately. So you can... Oh, there you go. Cool. Okay. So last time we basically started talking about noise. As I had mentioned, this is something we're going to be spending a bit of time on. So hopefully, you know, if you weren't here in person for that part of the lecture, you sort of took a look at that over the web. Where we basically ended up last time was, I think we essentially had covered all of the noise sources in MOSFETs, but I just wanted to kind of briefly remind everybody sort of how we go about doing some of these noise calculations, and we'll go through that in more detail as we go through today. So as I'd mentioned, where we sort of ended up last time was saying that if I looked at a MOSFET, then essentially, depending upon the region of operation, I could come up with what should the equivalent noise coming from the channel or from the conductive part of the MOSFET really be. And just to remind you, since we're mostly going to be working in the analog, or I should say the saturation region, we basically said that we were going to simply model that as being 4 kT gamma GM, right? Where that gamma factor, we said, includes all kinds of weirdnesses in it. So in the long channel device, it would have been 2/3, but in a short channel device, it may be more like 4/3 or something like that, depending upon exactly the physical mechanisms happening inside of there. But bottom line, from an analysis standpoint, that's how we were going to treat it, at least for the thermal noise part of things. Now, we also said that there was going to be some 1/f component associated with that as well. We talked a little bit about where that 1/f came from. And, you know, we looked a little bit about sort of how big that was going to be, how you treated that, essentially how you could figure out the total 1/f contribution. And if you've taken a look at the homework, you'll have seen that there's indeed a problem talking about that. But basically what we had kind of said was that most of the time in this class, we were kind of going to ignore this simply because we were working with relatively broadband types of circuits. And as long as we were working with these relatively broadband circuits, the relative contribution of that 1/f, typically speaking, was going to be fairly small. And by the way, in case you don't believe me, as I said, there's a problem in your homework to actually take a look at that, where you'd see essentially, okay, if I was supposed to operate the circuit over 1 second versus, let's say, over 1 week, obviously the longer you operate it, the longer you're going to integrate that 1/f noise. What you'd see is actually the amount you'd have to change the size of the FET, and therefore the amount of power you'd have to dissipate, was really quite small. Right? So basically, in most of the cases we're talking about, that's why I kind of claim that we can sort of ignore this 1/f noise. Now, that's not to say that that's a universal truth. Obviously, in some applications, that's going to be a really big deal, particularly in things where you're really operating at very low frequencies. But towards the end of the class, we'll talk some more about some techniques we can use to actually compensate or even eliminate that 1 over f noise. Okay? So this is really just sort of a reminder of what a small signal model might look like if I added in that noise source. And really there's nothing sort of magic there. It's sort of the same standard small signal model that you're used to, just where I've added in this noise current over here. And just as a reminder, I've done this double arrow thing just so that you guys to remember it's not a deterministic current source, it's noise. Okay, so you don't necessarily know, the polarity or anything like that. Okay? So again, just really to kind of remind everybody, if I gave you some circuit, which, by the way, I did in your homework, and it had, let's say, an active device in it, how would you go about doing a noise analysis? Now, by the way, you can actually do this in SPICE as well, and you'll be doing that in your homework. But obviously, we need to be able to do this by hand because we want to be able to get some prediction or really some understanding of what's happening and therefore how we can design our circuits to improve the noise performance. So just procedurally, if I give you some active circuit and you want to know what's the noise coming from that active circuit, then basically it kind of makes sense, right? What you essentially do is you take that circuit, and let me just give you an example. Let's say I have some common source amplifier, right? Then essentially what you do is you take that amplifier, you draw the small signal model, and only draw the sort of piece of the outward network here. So let's say there's some GMVI, there's going to be some noise source over here, right? And then that's going to be our output. And of course, maybe there's some capacitance or something like that over here. Okay? So you draw that small signal model. Then, since it's noise, and generally speaking, or in fact, always it should be the case, the noise has nothing to do with the input. Otherwise, it wouldn't really be thermal noise, or noise at all, I should say. Then basically, we're going to set all of the inputs to be 0. Right? Just, we're going to ground those out. Just this is like the standard superposition trick that we play, right? So then once I've done that, I just look at what is my output. In this case, let's say it's the output voltage, but in other cases, maybe you're interested in an output current or something like that. Then for each one of the noise sources that I have in my circuit, I'm just going to calculate what's the transfer function from that noise source to the output that I'm interested in, okay? So in this particular case, if I have a noise current and I'm interested in the output voltage, that transfer function would just be the impedance seen by the noise, right? Once I have that transfer function, then essentially what we're going to do is, and we'll see exactly, again in detail how we do this. If you remember, I had mentioned that, when we want to calculate the total noise at the output, what you essentially are going to do is you're going to take that transfer function. Let's just call it, in this case, we call it h of x. You're going to take that transfer function. You're going to do the magnitude squared, df, times whatever the noise source is. And you're going to integrate that from 0 to infinity. Okay? And again, we'll see exactly how we do that integral in a second. But once you've done that, that tells you sort of the total contribution from that particular noise source. Okay, and actually, let me just be careful. That's v of x squared, and that's, by the way, the spectral density. So again, if it's white, it's flat over frequency. If it's 1 over f, it has that 1 over f shape. But that's basically how you treat it. Okay? So now if I have, obviously, multiple noise sources, I'm just going to repeat this procedure, but just essentially by integrating a different noise source. Okay, and then at the end, I just add all those things together. Does this kind of make sense to people, or? Okay, now, as I've sort of noted on the slide here, conceptually this is really simple, but obviously it can get a little bit tedious if I have a really big circuit, okay? So what we're going to do is we're going to see we're going to go through a few examples, and I'll show you a few sort of tricks to help you figure out how you can do this relatively quickly, even with some more complicated circuits, okay? But again, the good news is you can actually sort of do some verification of all this using SPICE. There is this so-called dot noise analysis, and there's, of course, something similar in Spectre as well, where you can actually look at what is the noise being generated by a bunch of different elements. So just to give you an example here, I just took a MOSFET, and then what I'm doing is I'm looking at it's the noise current generated at its output, but the way I'm looking at that is that I just put this little current-controlled voltage source in here, just so that I could directly look at, in the voltage domain what the noise current was, rather than looking at, sort of trying to back calculate it from something over here. By the way, I did this with an ideal element over here because I wanted to grab the noise coming only from the MOSFET without, let's say, if I put just a load resistor or something like that, that resistance would also have some noise associated with it, right? So I'm trying to do this, kind of grab over here with an ideal element just so that I don't mess up the measurement that I'm interested in, okay? So I don't want to spend a ton of time on this because most of this should be fairly obvious. Again, if I've grabbed the MOSFET, then you can see for some low frequency region, I have this 1 over F behavior. Whereas at high frequencies, I'm just dominated by that thermal noise, okay? Now, there's just one other thing that's kind of interesting to notice here. So these are all relatively long channel devices, okay? Meaning, like, I don't have to worry about velocity saturation and things like that. All the things that you used to know about transistors, you can kind of apply here. So now here's the sort of interesting question. If you'll notice, if you look at the blue curve and this sort of pinkish curve over here, all I did between those two was take both the width and the length and multiply them by, in this case, 10. Okay? So notice, out over here where I'm thermal noise dominated, it looks like both of those basically have the same thermal noise density. So why is that?
Flicker is going to be worse with smaller area.
Well, I think you answered perhaps my next question. So, the first question was just, why is it that the thermal noise is actually the same for these two?
WL is constant, so GM is same.
Yeah, so basically I set the same W over L for both those two devices. And again, it's a relatively long channel. So because the W over L is the same, and presumably I didn't change the voltage bias, the GM is the same, right? So if the GM is the same, makes sense that these two lines right here have the same thermal noise density, okay? Now, so you shortcutted my other question, which was, well, okay, why is it that it's different down over here? Well, one of them just has actually 100 times larger area than the other, right? And if you remember with 1 over F noise, the larger your area, the more you sort of average the behavior of catching those electrons in the traps, and so the smaller the 1 over F noise ends up being, okay? So again, this is really mostly just kind of a reminder of what are the different noise sources and sort of how we go about doing the calculations, but we'll see some more detail in 1 second. So, any kind of questions on this? Or? Okay, by the way, usually somebody asks, something like back over here when I did this integral, like how I came up with these limits of 0 to infinity. So, since you guys didn't ask, maybe I'll ask you. Where does that come from? Why am I integrating from from 0 frequency to infinite frequency if I'm interested in sort of noise at the output of something? Why am I doing it that way?
Any transfer function you will roll off at high frequencies.
So you were saying something about any transfer function will roll off at high frequencies. I'm not sure about that. I could probably come up with a transfer function that would actually go up. So, and in fact, my question is even sort of simpler than that. Why did I choose 0 to infinity to begin with?
The mechanics of the integral.
Mechanics of, I don't know. Well, okay, I mean, I guess that's the pedantic answer. I'm not sure that's very intuitive. What am I really interested in when I say sort of the total noise at the output?
Instantaneous noise voltage.
Okay, instantaneous noise voltage. There was somebody else who started saying something.
Power?
Power, is that what you said? Yeah, okay, so you might say something like, oh, there's a Wiener-Khinchin theorem, and if I have noise and I want to know what the total power is, I have to integrate from 0 to infinity. That's correct. I like Dan's answer a little bit better, right? If I'm interested in kind of what's the instantaneous noise voltage at a particular point in time, and I can move that time by a femtosecond in either which direction, or whatever, an attosecond, or whatever arbitrary thing we want to come up with. So what I'm kind of interested in is, over all previous time up until now, what was the noise sort of doing to me, right? And by the way, just as a reminder, this integral here is actually kind of the way that we're going to figure out, and really I should say the integral including that transfer function there, that's kind of how we're going to figure out what's really the bandwidth that we're working over. Right? Because if you remember I had said in the beginning, noise was always kT times some available bandwidth. This integral over here is really how we figure out what is that available bandwidth. Because obviously in our circuit, there's nothing magic telling the circuit, okay, this is the bandwidth you care about, right? It's going to be set by, as an example, some resistors, capacitors, etc. Okay? So let's actually take a look at the implications of that on a real circuit that you might actually care about. Okay, so with that, let's actually switch over to the next thing, which is now we're really going to do some more of these noise analyses and see what they imply from an actual circuit standpoint. Okay? So, turns out the most sort of, at least initially, interesting thing to start with, just because it gives us a lot of intuition about things, is let's just pretend I had this very simple thing. Okay, that, by the way, you might use in an analog to digital converter or actually in a whole bunch of other circuits as well. So let's just say I was interested in basically taking a snapshot of some input voltage. Okay, so that's the so-called sample and hold. So just in case you haven't seen something like this before, the idea is, let's say I have some input that's doing this, and I just want to grab it at a particular point in time. So that would be sort of my output over here. Then what I would do is I'd turn that switch off, so that right at that point in time, basically I'm going to hold that voltage right there. Okay? And of course, it should stay there until I again turn on the switch again, and the circuit starts tracking the input one more time. Okay? So again, this is something you might do like in an analog to digital converter, or maybe your oscilloscope, or actually a whole bunch of other places. But as you can imagine, any real switch that I build has some resistance associated with it. And that resistance, of course, has some noise on it. Okay? So that means that even though I wanted to grab exactly this voltage at that particular point in time, what's going to happen is if I really look at it there, and maybe I'll do it in a different color, if I really look at what I actually ended up sampling, there would be some noise on top of this. And right when I turn off that switch, I'm just going to hold that noise sample forever, right? Because once I turn off the switch, no current can be flowing, and so I've just sort of sampled that noise voltage onto the capacitor. Okay? So, if we want to figure out what is the actual noise we're going to get, again, we can just sort of follow our simple procedure. Right? So we say, okay, fine. I'll ground out the input, because that kind of doesn't matter, right? And what I'm going to be interested in here is, while the switch is actually on, so I'll draw sort of the equivalent circuit there, while the switch is on, what is kind of the equivalent circuit that I have, so that I know right when I turn off that switch, if I know sort of what the variance of the noise is for when the thing was on, that should be the noise that I sample, right? So let's just draw that equivalent circuit. So I'm going to have the noise voltage, from the resistor, right? I'm going to have that resistor. And then I'm going to have that capacitor that I'm driving, okay? And again, the whole trick is that since I'm just going to arbitrarily turn that switch off at some point in time, what I'm really interested in is what's the variance of noise I'm going to sample at the output right there, okay? And again, since I'm sort of doing that instantaneously, I have to do it sort of over all previous time until now, right? Where now could be like instantly fast, meaning that's why I sort of do that integral from 0 to infinity, okay? Well, so if I have that circuit, it's actually pretty easy to figure out what's the output voltage going to be, right? So remember the noise source, that's just going to be invariance for kTr. And of course, there's a delta F there if I want overall frequency. But the power spectral density, so Vn squared divided by delta F, that's just 4 kTr. Okay? So I just take that, and now I just have to pass it through the transfer function from that point to the output. So by the way, what is that transfer function?
1 divided by 1 plus SRC.
Yeah, there we go. That's one of the simplest things. Hopefully you learned a bazillion times by now. That's just going to be 1 over 1 plus SRC, right? It's just a low-pass filter. Okay. Well, so now what I have to do is, if I want to know essentially the noise density at a particular frequency, then just like is written right there, I'm going to say that it's just 4 kTr, that's again just the input noise density, times the magnitude of that transfer function squared. Okay? And so if I want to know the total noise, again, I'll just integrate this whole thing from 0 to infinity, and magically, this is the result you get. Okay? So the magic final answer is that the total noise at the output is just going to be kT divided by C. Okay? Now, sometimes when people sort of foresee this, they're a little bit surprised and say, hey, wait a minute, what the heck's going on here? The resistance is the thing that was generating noise in the first place, but I seem to have come up with a result that says that the total noise at the output is totally independent of the resistance, right? And again, this is the variance of the noise at the output, and seems to be just completely independent of resistance. The only thing I can change here from a circuit standpoint is the cap, right? Because Boltzmann's constant, again, I can't do anything about that. Temperature, usually I can't do anything about that. Cap is sort of my only thing I can play with here. So, why is it that we got this magic result that it doesn't depend on the resistance at all? Anybody have an idea or seen this before, perhaps? Yeah, Brian?
I mean, it's as you increase the resistance, you both decrease the noise and you increase the noise and you decrease the bandwidth.
There we go.
So you're counteracting.
Exactly, right? So the classic explanation here is, and this is kind of shown on the next slide, is basically that as you increase that noise, you increase the density coming out of the resistor, meaning the voltage noise density coming out of the resistor, but the bandwidth gets smaller. Okay, and what this plot here is showing is just these are the two sort of transfer functions, or really these are the two sort of noise profiles versus frequency. And then the red and the kind of pinkish curve or purple or whatever that is, those two are just showing as you integrate over all frequencies, what does the total become? And so what you can see is indeed, if I have the larger resistance, I start out from a higher level, but I flatten out earlier. Whereas if I have the smaller resistance, I have a lower initial level because the resistor is smaller, but I have a wider bandwidth, so if I go out to sort of infinite frequency, I get the exact same noise density. Okay? So exactly like we were saying, it's just really that the effective noise bandwidth in this particular circuit was really just being set by 1 over 4 RC. Okay, and since the bandwidth was inversely related to the amount of noise we had in the first place, that's why it turns out that actually it's only the capacitance that matters. Okay? Now, that's actually the sort of typical circuits explanation. I claim there's actually even a couple more, perhaps even more intuitive ways of explaining why it should really be independent of the resistance. So anybody have any thoughts? How else could you maybe see that? And I'll sort of give you a hint, which is just the title of that slide. So how else might you see that all that really matters is capacitance? Any thoughts?
E equals CV squared equals KT.
Ah, okay. So now we actually have to get a little bit tricky. So you said that the energy stored in a capacitor is 1/2 CV squared, right? So now the only minor annoyance is, well, by the way, just as a reminder, what did we say was the energy available from thermal noise?
KT.
It's KT, right? Okay, so now the only minor annoyance is if I set these two equal to each other, and by the way, I really did this with lowercase v intentionally, right? So I said, hey, if the energy stored in the capacitor should be the same as the energy coming from the thermal noise, then I should get just that 1/2 CV squared is equal to KT, right? Now again, the only minor annoyance here is that if I carry that out, what I'm unfortunately going to get is that the noise square, or the noise sigma, is 2 KT over C. So, what went wrong? Yeah, there we go. So just as a reminder, for those of you who were either in 141 or took 141 at some point, right? The simple way to think about this is the following. If I want to get a certain voltage on that capacitor, then the charge I need is C times V, right? Well, guess what? If I have a voltage source of V, and somehow I end up with that voltage on the capacitor, right, then I have to pull off that amount of charge, which is just C times V. Well, if that voltage source had a value of V, the energy that came out of the supply was C times V squared, right? Because, of course, it's just the charge times the voltage. Well, so now if I actually follow that through and I say, okay, the energy that came out of the supply was CV squared, and that energy is equal to the amount I have from thermal noise, now we'll get the right result, right? Now we'll actually get that CV squared is equal to KT, which of course means V squared is equal to KT over C. Okay? By the way, just maybe to do a quick poll, has anybody ever heard of the equipartition theorem? No takers. Okay, well, go home, look it up. It's another sort of quick way of actually getting this exact same result, because it tells you that for every degree of freedom, there's KT over 2 of available energy. Okay, and so if you set that equal to the energy stored in the capacitor, you'll again get the KT over C result. Okay, not too important. It is somewhat useful just because it turns out that almost any electrical circuit you work with, the final result for noise is going to end up being something like KT over C, perhaps times some scale factor. But, in case you're curious, go look it up. You'll see sort of where that comes from. Now, actually, just because it's sort of fun and, you might run into it in something like a midterm or a prelim exam, based on everything that we just said now, let's see if we can actually figure out one more interesting thing. So let's say I had a circuit where I had an inductor. Okay, and so just like before, here when I had a capacitor, I was going to try and store sort of a voltage onto that thing. So now what I'm going to try and do is store a current in an inductor. Okay, I'm just interested in sort of, I'm kind of doing the sample and hold just in the current domain. Okay? So, without doing any integrals or anything like that, what's the noise current density, or actually the variance of noise current, I'm going to store in that inductor, or that I would sample in that inductor?
KT over L.
Yeah, okay, well, so why is it KT over L?
Because the energy stored in a inductor is L I squared.
Right, exactly. So the energy stored in the inductor is Li squared, right? And we're going to throw away the factors of a half for the same reason we threw it away in the voltage domain. So if I'm going to store Li squared in the inductor, and the thermal noise I have is KT, thermal noise energy, of course, then guess what? Just like before, I should end up with KT over L noise current stored in the inductor. Okay? So now just because you got that one so quickly, now let's even do maybe one more thing. So again, I'm going to do sort of a sample and hold. But now I'm going to put an L and a C in parallel with each other. And again, what I want to know is how much noise voltage variance am I going to get at the output of that LC circuit. This one's a little bit more of a brain twister.
KT over the square root of L times C.
Unfortunately, the dimensions of that don't quite work out, right? Because that's KT over frequency. So but you're kind of thinking in the right direction. This one's really a trick question, by the way. So.
Really?
What's that?
Q is infinite, right?
The Q is infinite. I claim I can still actually evaluate this thing perfectly well and tell you the answer. You're right, the Q is indeed infinite, but that also means the bandwidth is 0, so.
No noise?
No, still going to have noise. I'll give you a hint. Okay, well, there's a KT in there. I agree with that. What else is there? What's going to happen when you store a little packet of charge onto that thing? Just intuitive, I just dump some little charge onto that inductor, and then I let go of the switch. What's going to happen?
You know,
It's going to circulate.
Yeah, it's going to jump back and forth, right? Okay, I agree with that. So, as it's jumping back and forth, what's the energy sort of, what two forms is it being sloshed between?
Current and voltage.
Current and voltage, yeah. It's being stored as either charge or magnetic field, right? Okay, so now, here's the magic bullet. Did the amount of energy I'm going to store in the capacitor change any?
No.
Didn't, right? Okay, so what's the answer?
KT over C.
Bingo, it's KT over C, right? Because even though I threw this weird inductor in there, all that did was just slosh the thing back and forth, right? But on average, if I just kept sampling the thing, sometimes it's going to be all stored as charge, and exactly the same variance as I had before is what's going to happen there. Good. Does this make sense to everybody? Or, as I said, this is more of the trick question, but it's kind of useful to think about because a lot of times you can take certain circuits and just look at it and say, okay, I know what the answer should be. And by the way, if you're ever in doubt, KT over C is always the right guess. Okay? Any questions? Okay. So we kind of went through this, useful example. I flipped around the orders of the slides a little bit here. So this, I think, used to be slide number 8 or 9, something like that. So you can flip to that in your lecture notes. Now, obviously, I kind of gave you these fun examples, but where the answer was quote unquote easy. But in reality, I'm going to give you some actual circuits, and you're going to need to know how to actually evaluate those integrals of basically these transfer functions squared from 0 to infinity. Trust me, doing the math for those can this one is pretty easy, but all of the rest of them get a little bit annoying. So the good news is I've given you all those integrals. Okay, and I claim I've given you all of those integrals, even though I've only shown you things up to second order here, simply because you can always take a more complicated transfer function and decompose it into a bunch of second order systems by doing partial fractions. Okay, and not that I'm expecting you to do that a bunch of times, but basically I claim that once you have all these, you're done, you can create everything else that you're interested in. Okay? So as we you may have already seen before, if I just have that first order system where I'm characterizing it by just a single pole at omega naught, when I do that integral, what it basically tells you is the effective bandwidth of that system is omega naught divided by 4. Okay? By the way, why is it divided by 4? Intuitively, why is it sort of smaller than omega naught? Anybody have any ideas? Why wouldn't I have just said that the bandwidth is only omega naught? What do you guys think? Let's maybe do a little sketch of that transfer function. Okay, so once I hit omega naught, how fast does that thing roll off? In just the linear, if I just plotted the magnitude of h of f. Okay? Oops. Versus frequency. How fast does that thing roll off?
20 dB per decade.
Yeah, just 20 dB per decade, right? Okay, so now, if I square this thing, does it roll off faster or slower?
Faster.
Yeah, faster, right? So basically, if I, it's obviously there's a 3 dB point over here, but now what I'm really going to get is something that looks kind of like that, right? Well, so because it's rolling off faster, then basically that's why there's that factor of 4 there, okay? Because the effective bandwidth is sort of being reduced just by the fact that I'm rolling off that quickly, okay? Now, by the way, if you want to be really technical about it, this becomes actually pi f naught over 4, which is only slightly less than 1, right? Because omega naught is, of course, 2 pi f. But bottom line, it's just because when I square it, it's going to roll off faster than sort of what I would have thought if I was just looking at the magnitude. Okay? Now, so by the way, just, this should already give you a hint. this means that if I have a higher order transfer function, meaning with more poles in it that rolls off even faster, then kind of the reduction in that bandwidth should be even sharper. Right? Now, so that's kind of a useful, intuitive thing to think about. Again, if we want to actually do some of these calculations, we need some of these integrals. Good news is, even those integrals are also actually pretty easy to deal with. Okay, so what I'm showing here is just sort of your standard second-order low-pass filter, or second-order system, I should say. Right? So here I have no zeros in that transfer function. And the good news is, if I do this integral, what you're going to get is just omega naught q divided by 4. Where, by the way, this omega naught q, that's basically just this term in the center over here, right? So whatever term multiplies the linear s in the denominator, just take 1 over that and divide it by 4. That's what the integral ends up being, okay? So that's just kind of a quick shortcut for looking at these things. Now, once I've done this, actually I claim that it's pretty easy to get this. Okay, simply because it turns out these two integrals are the same. Okay, meaning this thing that has no zero in it and this one that has the 0 at 0, they turn out to have the exact same integral. Okay, so once you know these two, I can add in a 0 and you get this answer really quickly. Right, because basically that omega naught q over 4, that's kind of just this piece right here. And then this thing that has the 0 in it, all you have to do is figure out what the ratio between that 0 and omega naught is. And then since we're squaring it, that's where you come up with this piece right here. Okay? So if you don't happen to remember this, just remember that one, and you can always get back to what should happen with the 0. Okay? Does this kind of make sense to people, or? Okay. So now that we've got that, kind of useful to maybe go through a couple of examples. Okay, so the first example I wanted to go through was just this very simple common source amplifier. Okay, so as usual, that's the input, that's the output. If I just sort of follow my procedure, first thing to do is just draw the small signal model. Okay? So and now, by the way, I'm going to ignore all the capacitive parasitics of the input just to make my life a little bit easier here. Okay? So what I'm going to have is, I'm going to have the GM from the transistor, right, times some input voltage. I'm going to have the load resistance. I have the load capacitance over there. And then since I'm interested in noise, I'm going to add in my noise sources. Okay, so I'm going to have, some noise from the transistor, right? Let's call that IN of GM. And I'm also going to have some noise from the resistor, right? Okay, so now, usually at this point, I sort of take a shortcut. So, since I have these two noise sources, meaning one from the GM and one from the load resistance, they just they show up in parallel, right? So that means they're going to see the same impedance looking over into the actual circuit, right? So rather than kind of keep track of those separately, I'm just going to lump them together. The only thing you have to be careful of is, remember, I'm going to add them in variances, not in magnitude. Okay? And so, since I know that this one from the GM, right, we said that that's just going to be 4 kT gamma GM. And from the resistor, that's just going to be 4 kT over RL in terms of density. All right, so when I add those two together, that basically just gives me that piece right there. Where, by the way, for gamma, I just assumed it was 2/3. Whenever you see that 2/3 there, just in the back of your mind, pretend that that's gamma. Okay? So that's the noise density coming from my noisy elements. And then, of course, the only thing left is to multiply it by the impedance seen by the circuit squared. Okay? Well, that's pretty easy. The impedance is just RL over 1 plus SRLCL, right? And so now, just to sort of manipulate this a little bit into the integral form that I remember, I'll just pull out that RL in front. So that's just going to be RL squared. And then I have the integral of the standard transfer function that I'm used to, right? Once I've done that, that integral, if you don't remember, you just go back and look at your trusty table. But for a first order thing, it's really easy. It's just omega naught divided by 4, okay? And omega naught, of course, is 1 over RL times CL here. So that's how I come up with this. And then now, actually, nicely enough, a bunch of things get much simpler, okay? So obviously, if I just, manipulate this thing a little bit, notice I'm still going to have this KT over C, right? I just pulled that out. The two 4s cancel each other nicely enough. And so now all I do is basically this RL cancels with the squared right there, and then I just push it inside. And so what I'm going to end up with is something that looks like this. So it's KT over C times 1 plus gamma GM RL. Okay? Well, even that should actually look very familiar to you. You say, oh, well, hey, GMRL, that's just the voltage gain of the circuit, right? So I should just get something like KT over C times 1 plus gamma times the voltage gain, okay? So by the way, this kind of result here is really, really common. So that, remember I said before, guessing KT over C is almost always a good guess. Proof, once again, KT over C just magically shows up all over the place, okay? In this case, it's scaled by the voltage gain, since we have that active element inside of there. But it's still basically KT over C. So because this form is really, really common, a lot of times what I will do as a shorthand, and you might see in some books as well, is I'll just say that for this particular amplifier, the noise at the output is this KT over C times some noise factor, or NF, okay? Where that NF is just sort of capturing, how much did you multiply the KT over C by, given that I have this particular amplifier here, okay? Does this sort of make sense to people, or? Nope. Okay. So if that makes sense, then now actually we'll do something a little bit more fun, which will also be useful from the standpoint of your homework to just go through this exercise. So what I'm going to do now is let's try and actually go through a two-stage amplifier. Okay, so I'm basically just going to take two of the same amplifier I had before, and I'm just going to cascade them. Okay, so the circuit I'm interested in, just going to look something like this. Okay, and of course that's the input, and that's the output. Okay, so now you guys tell me, how should I go about handling this one in terms of calculating the noise? What's sort of the first thing I should do? Say that again?
Small signal circuit?
Yeah, so the first thing I could do is just basically draw the small signal circuit, right? Okay, so let's quickly do that. So just like before, I'm going to have some GM over here. That's times some input voltage. Then there's some load resistance. There's some load capacitance there. Let me just call this V mid. Okay, so there'll be some V mid over there. And then I'm going to leave myself some space just because we're going to add some stuff in a second. Then I'm again going to have that GM V mid. Some load resistance over here. And some load capacitance. And the output voltage. Okay. So I've got my small signal model, and we've got noise to help us with this calculation now here too. So what's next? What should I do?
Find the noise of each stage and then sum them.
Yeah, okay. So the next thing I would do is basically start adding in noise sources, right? So let me actually start in a somewhat reverse way just to make life a little bit easier. So I'm going to claim that the first noise I'm going to want to add in is actually over there. So why might it be that I wanted to add the noise at the second stage first?
First stage is more complicated.
Yeah, actually that's exactly right. So I added the thing at the output over there because the first stage is more complicated, right? So I'm just going to add the thing at the output because guess what? I claim you already know this answer, right? We just did that right here. Okay, so just as a reminder, what is that answer going to be? So if I just looked at the output noise due to the second stage, what would that be?
KT over C times NF.
Yeah, it's just going to be KT over CL times, and then just to be precise, 1 plus gamma AV, right? Okay, so now, we said the first stage is more complicated. Why is the first stage more complicated?
Do you get noise coupled back from the second stage?
So I'm going to ignore like the capacitors coming from the MOSFETs. So don't worry about those for now. So let's just assume, from the signal standpoint, the small signal model really does look like what I drew here. Okay?
There's a gain factor.
Okay, there's a gain factor, right? So by the way, if there really was just a gain factor, let's assume that that was the case. So we could just say, okay, I could model this as being something like I have my first stage, right, like this, driving some gain and going to the output, right? And let's say that I even tell you the gain of that. Let's call that gain AV. If that was my model, what would I claim the noise at the output should be due to the first stage?
KT over CL NF times AV squared.
Yeah, it would be KT over CL times that NF times the gain squared. Does everybody see that? Or? So it's just the gain squared, because I'm assuming that this gain stage over here is some perfect gain stage. And if I had a certain noise variance over here, if I multiply it by a gain, then the variance gets squared, right? Okay, so it turns out that's almost right. What's the problem?
The noise
Yeah.
was shape in the first stage.
There we go, right? So the problem is that unfortunately, I'm not just passing it through a perfect amplifier, right? What I'm actually doing is I'm filtering it again, okay? So this is a key thing you have to keep in mind because it's really tempting sometimes to do exactly what we just drew here. But remember, anytime I filter the noise again, I have to do that whole integral, okay? So what you'd really have to do here is write out the transfer function of noise that sits over there and how it gets to the output voltage over there, okay? Now, the good news is it's actually pretty easy in this case. And in fact, let me maybe ask you guys. So if I have a certain noise current over here, what is the transfer function to get to the voltage output over there? So let me call that IN1. So what is that transfer function? And by the way, you can decompose it pretty easily. What do you guys think?
RL divided by 1 plus SRC
Right?
squared.
Almost. Okay, so that's the impedance of the first stage, right?
GM.
Okay, now if I want to get to the second stage, so this first thing here is just going to tell me per unit current how much voltage I get on Vmid, right? And so now if I want to get to the output, I just multiply it by the transfer function of that second stage, right? Which is of course just GMRL divided by 1 plus SRL CL, right? Okay, by the way, I ignored the signs here. Be more careful than me. Turns out here it doesn't matter, but I just in case you're wondering. Okay, so that's the transfer function. The good news is that actually that one's really easy because that's just, the thing on the bottom is just 1 plus SRL CL squared. And it turns out that if you go and you look again at your trusty integral table, just as a reminder, when you do those integrals, all that matters is this term in the center over here. Okay? Well, that one's just going to turn out to be 2 times S RL CL, right? Because if I just do the thing on the bottom squared, that's exactly what you get. So if you do that whole integral all over again, the piece you'd get coming from the bottom would just be 1 over 8 RL CL. Okay? Now, I'm not going to walk through all the rest of the example because I think once you have this, you can actually figure things out. But basically what would happen is rather than, the noise from the first stage would look a lot like this. It's just that rather than having only this NF over here, what would actually end up happening is there'd be a factor of 2 on the bottom there. Okay? And that factor of 2 is just coming about because basically with that second order transfer function, or really with that double filtering, the effective bandwidth would get cut down by a factor of 2. Okay? This kind of makes sense to people, or? So the purpose of this going through this example was kind of twofold. So one, it's just to give you an example of how you go about mechanically doing these calculations. But two, actually it should sort of give you some intuition into how these types of things behave. And that's particularly useful because if I start giving you really complicated networks, it's really nice to be able to just sort of intuitively guess what the answer should look like. Okay? There's an example here. How would this factor of 2 down there, how would it sort of change as I change the bandwidth of this amplifier in the second stage? As an example, let's say that I made the bandwidth of that amplifier in the second stage really, really big. What would happen to that factor of 2? Would I divide the noise by more than 2, less than 2? What would I do? What do you guys think?
Less than 2.
Yeah, less than 2, right? If I had an infinitely wide band second stage, then literally all I'm doing is taking the noise from the first stage and multiplying it by the gain, right? Because I'm not filtering it anymore. So similarly, if I made the bandwidth of that second stage really, really narrow, in the limit, if I made it sort of 0, I'd be throwing away all of the noise from the first stage, right? Because I'd just be totally filtering out. None of it would actually make it to the output. Okay? So again, it's kind of useful to go through these exercises because, okay, A, you just see how to do the integrals, but B, it gives you an idea of what should you expect to have happen, right? How should the sort of things be related to each other? In fact, I'll even give that to you as sort of a little bit of a homework. You can go home and you can write out a very simple expression that would tell you how does this thing depend on the ratio of the bandwidths of the two stages. Question?
For the noise contribution of the second stage, AV is the gain of
the second stage. That's right. Yeah. Yeah. Any other questions on this? Or? Okay, so as I said, you're going to have a whole lot more fun doing this in your homeworks because you're going to be doing this many, 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 many times. So, I guess get used to it, but it's not too bad. Like, once you get the hang of it, it usually goes through fairly smoothly. So, with that, since we spent sort of a little bit of time just kind of going through how do you calculate noise and, what does that look like, I wanted to spend a little bit of a side note on just kind of looking at the implications of all this, okay? So in particular, let's kind of go back to that example that we had where we just had the very simple sample and hold circuit, right? Where we just had basically some switch that we were sampling a voltage onto a capacitor, okay? So what's kind of interesting to look at is if I'm going to do that sampling, obviously I don't really want the noise, right? That just sort of corrupts my signal. So a lot of times what you're interested in is basically how big is that noise relative to the signal that you're actually interested in. Okay? And usually the way people look at that is the so-called signal-to-noise ratio. Okay? And what they mean by a signal-to-noise ratio, and by the way, the units of this are a little bit funny, but they usually say something like it's the power of the signal divided by the power of the noise. Now, since we usually work with voltages, when they say power, what they really mean is variance. Okay, so what they really mean is something like the variance of the signal divided by the variance of the noise. Okay, so as an example, let's just say that I had a sinusoidal signal at the input with a certain 0 to peak amplitude, then basically the variance of that input signal would be just 1/2 V0 to peak squared. Okay? And so let's assume that I'm dominated by thermal noise. Let's say maybe I have an amplifier or something driving the sample and hold, right? Then basically, as we had said a few times now, the noise variance, meaning in voltage squared, is just going to be kT over C times that NF. Okay? So now I can already actually see something pretty interesting. So if I want to know what is my signal to noise ratio, then I would basically just take the ratio of these two quantities, right? Which would give me 1/2 CV squared divided by NF times KT, okay? By the way, intuitively, this should kind of be appealing because I have an energy divided by an energy, right? So it's going to tell me this CV squared, that's kind of like the energy of the signal. And that KT, that's kind of like my thermal noise energy, right? But now, notice one thing. This is in SNR, right? So if I want to increase the SNR by basically a factor of 4, that means I have to increase the capacitance by a factor of 4, okay? And remember, this is in power, meaning in variance. So for every 6 dB improvement in SNR, I'm going to need a factor of 4 more capacitance, okay? Now, why do you guys think I'm sort of stressing this so much? Why is that important?
Speed.
Okay, speed, you're right. But actually, indirectly, that's going to translate into something else, too.
Well, increasing cap by 4 means increasing GM by 4, which means increasing current by 4.
There we go.
Which means increasing power by 4.
There we go. Okay, right? So if I want a certain speed, then basically, if I want to get a better signal-to-noise ratio, I have to up the cap by a factor of 4, which means the GM has to go up by a factor of 4, which basically means the current has to go up by a factor of 4, right? That's pretty nasty. And actually, as we'd even talked about this a little bit before, it's particularly nasty when you sort of think about it in comparison to what happens in digital. Okay, now, to make that comparison, what we have to remember is that in digital, if I add one more bit, that's kind of like saying that I have a factor of 2 more resolution in what I can sort of figure out is the smallest quantity. Or equivalently, if I added one more MSB, that's kind of like saying that I'm doubling the range of things I can handle, right? If you kind of think about that, you can sort of translate the number of bits that you have into an effective, like, almost in some sense, noise, right? Because just if we sort of think about something simple, let's say that I had a sinusoid, and then I just quantized it, right? So I have something that looks, let's say, like this. Well, okay, my drawing's bad, but you get the idea, right? What I can basically say is that because I quantized that thing, I basically have some errors, right? I've made some mistakes. So, like, during this entire time, like, I'm wrong by something like, you know, the quantization step divided by 2, right? So if I'm interested in being really, really precise, I can translate that into an effective noise, okay? I could kind of argue that, you know, this is sort of like, again, just taking away from how precisely I really know the signal, okay? So you can do some simple math. It's, you know, not too complicated. If you assume a uniformly distributed signal and that the quantization is perfect and etc., you can come up with a noise variance for that quantization process. It just tells you that noise variance is delta squared over 12, where delta is just the size of those quantization steps, okay? So why am I going through this whole thing? Because what this basically tells you is something actually sort of similar to what we'd already seen, which is that essentially the noise power, the noise coming from that quantization, if I add just one more bit, because there's this delta squared over here, that noise power will go down by a factor of 4, okay? So that tells you that if I'm in digital, or if I want to get one more digital bit, the signal-to-noise ratio that I need goes up by a factor of 6 dB, right? Okay, so I claim this is actually sort of both good and bad news. So if I'm a digital guy, this is kind of good news, right? Because I just say, okay, well, great. If I want to get a factor of 2 more precise, I just add one more bit and I'm done, right? End of story. Well, if you're an analog guy, this is really bad news, right? Because then you just start, you can look at this table really quickly and say, oh, okay, if I want 8 bits, then I only need 60 dB SNR, or excuse me, even 50. Right? If I want 16 bits, it's only 98 dB. That's only an extra 40 dB. Right? And by the way, of course, the joke here is that if you're in dB, 40 may not sound like much, but remember that's a factor of 10,000 in power. Right? Not so nice. If I wanted to build a 32-bit analog precise thing, actually I don't even remember what that number is, but it's like 4 to the 32, so it's like, 2 billion squared. I don't even know how to call the thing in front of that number, right? So, by the way, that's why there is no such thing as 32-bit precise analog stuff, right? Because that's freaking expensive, right? That's hard to do because, remember, as we just said, if I wanted any kind of speed at all, I'd have to take, if I took from, let's say, a 10-bit thing to a 32-bit thing, I'd have to multiply by capacitance value by 4 to the 22. Again, I don't even know what that number actually is, so I'm not even going to bother trying calculating it. But basically, you can actually pretty quickly calculate that, if I had a certain size chip, and I just filled that entire chip with capacitance, and I have a certain supply voltage I can operate, you can very quickly calculate what's the maximum number of bits or effective bits you could actually get out of your analog circuit. Right? Because it's just, that total maximum capacitance times voltage squared, that's kind of the best you could do, right? And by the way, for a modern technology, that's maybe, 13, 14 bits, somewhere in that ballpark. It's not super high, okay? So again, really the point here is that when you're talking about analog and you're talking about getting more precision, it's very, very expensive from a power standpoint. When somebody says that they built a 9-bit precise thing, and you said, oh, well, that's not so hard. I mean, I built an 8-bit precise thing. Remember, there's a factor of 4 there. Okay? So it's not just like it was sort of for free. Okay? So obviously the other point here is that because it's so expensive to actually get better signal-to-noise ratio, it's a really bad idea to just grossly over-design stuff. Right? Because that means the penalty you're going to pay is really, really sharp. And so that's why we're actually spending a lot of the time now to really try and understand what is the noise performance of our circuits going to be. Because once you get into this regime, you really want to get that analysis right. Because if you don't, you're going to be paying for it very dearly, either in terms of way more power, or just your performance is going to be nowhere near what you expected it to be. Okay? Does this kind of make sense to people, or? There you go. Exactly. Your advisor or your boss, whoever it is, will fire you because you didn't get the performance you were supposed to. That's exactly right. I should use that more often. Okay. So, just to kind of quickly wrap up on this particular topic here, and we'll talk a little bit more about noise in one last context probably next time. So, oftentimes, if you're building some general purpose op-amp or something like that, you kind of want to give people an idea of just what is the noise performance of your particular part, right? Because, if somebody wants to use it for, let's say, an RF receiver versus a sensor or whatever it is, they usually want to know, okay, what is kind of the noise performance of this thing going to be? Okay, and if we kind of think about it, there's a couple ways we might be able to come up with to specify the noise performance. Okay, so let's just say I have some general purpose op-amp over here. So there's kind of one of two things I could do. Now, by the way, usually you're going to specify these things in terms of the noise densities, because if I'm just selling you the amplifier, you don't necessarily know what circuit's going to be hooked up around it, right? You don't know what the bandwidth of that circuit's going to be, so I kind of have to tell you the noise density to begin with, okay? But I could kind of tell you either one of two things. I could either tell you the output noise density, right? Or I could tell you the input referred noise density, right? So, if you guys were going to buy a part and let's say part number 1 was spec'd with the output noise and part number 2 was spec'd with the input noise, which one would you choose? Or which one would you, figure out more quickly which one you actually wanted?
Input.
Input. Who else thinks input? Okay. Anybody for output? Okay, no brave souls. So I kind of agree input, but now why input?
Calculate SNR right off the bat.
Okay, that's kind of one way of saying it. It's, if I know how big the input signal is, I could figure out the SNR pretty quickly. I basically agree with that. Any other thoughts?
You're going to give some input to the amplifier, so if and that signal is going to have some noise associated with it. So if the noise from the amplifier is much more than that, then you won't use it.
Yeah, I think you're kind of saying the same thing as Brian. You're saying, well, usually I know something about the input signal, and so if I know something about the input signal, I can kind of calculate what that noise is, right? Any other thoughts?
Well, we just calculated that the output noise depends on the gain, and so it would depend on how you had it configured.
Ah, there we go, right? So we just did a calculation that said something like the output noise was KT over C times 1 plus gamma AV, right? Now, this is obviously the integrated output noise, but it depends on the gain, like you said, right? So actually, there's even a kind of more direct tie into this. So let's just say I really do have my MOSFET common source amplifier, and obviously this is a grossly oversimplified model for what's inside of this, but in terms of noise performance, that basically gives you the right answer 90x% of the time. And we'll talk some more about exactly how it gets messed up, okay? So let's say I have my MOSFET amplifier there, right? So in fact, I'm not even going to put a current source there. I'm just going to put some arbitrary load impedance, okay? So if I draw the small signal model for this thing, I have some GM times the input voltage. Then I have some arbitrary load impedance, right? Then I'm going to have my noise current, right? And actually, for now, let's just even pretend that arbitrary, load impedance, let's pretend it's ideal so it doesn't even add any noise, okay? Because a lot of times, that's not going to be the biggest factor. So, if I wanted to figure out what this input referred noise was in voltage, anybody know? How would I do that? What would it be? Particularly if I want a noise density. How would I input refer this noise current back to the VI? What do I do? Somebody other than Will. And Dan will exclude you just because you're sitting next to him.
Guilty by association.
Exactly. So, how do you input refer that thing?
Divided by GM square.
Yeah, I just divide it by the gain, right? So in this particular case, I would say that the input noise is just the output noise current divided by GM squared, right? Because that's just how I translate from input to output. Notice the load impedance didn't matter at all because it scales both the signal and the noise by the same amount, right? Okay, this is actually kind of nice because remember that noise current is just 4 kT gamma GM, right? So if I want to know the input referred noise voltage, then all I'm going to get is 4 kT gamma divided by GM, okay? So actually I would kind of claim this is sort of the principal reason you want to look at the input. Because if you look at the input, whatever I've done on the load, which by the way usually varies all over the place, in terms of the input noise density, as long as I have a reasonably well-controlled GM, which oftentimes is basically the case, I basically should know what that input referred noise density is. Okay? Does this kind of make sense to people, or? Okay, so now maybe just to make sure it actually makes sense, if I told you just the input referred voltage noise density, is that in general the end of the story, or do I have to tell you something else too? By the way, again, this is just some arbitrary op-amp. What else might I need to tell you?
Output impedance?
Well, if I'm always focusing on the input noise density, then I've kind of just claimed that maybe I didn't even need to know the output impedance, at least for a MOSFET amplifier. But actually, indirectly tied to that, what else do I need to tell you?
Current noise density.
Ah, there we go. I might have some current noise density too, right? So in fact, in general, if I want to specify some amplifier, which here I'm just going to be looking at 2 ports now, but just think of it as an amplifier. In general, I really need to tell you 2 things, right? So one is, what's the input referred voltage noise density? And the other is, what's the input referred current noise density? Because remember, even though for MOSFETs we've claimed that the input impedance is infinite, at least at DC, A, I wouldn't necessarily be using a MOSFET, and B, I could always be adding some other elements in front of there that actually would not make that the case anymore, right? So I might have some noisy source at the very input that actually generates some current noise, okay? So in general, if I want to take some arbitrary circuit, some arbitrary 2-port, I'll always add in the voltage noise density and the current noise density, okay? Now, by the way, in general, this voltage noise and this current noise might actually be correlated with each other. For now, let's ignore that. I'll come back to it in 1 second. Okay, so for now, let's just pretend I can specify each of these 2 completely independently of each other. Okay, so let's say you went and you bought some amplifier and you wanted to test if really the specs they gave you were correct. How would you actually go and measure the voltage noise and the current noise? What would you do? Heard somebody say it. What do you do if you want to measure those things?
Ground gate?
Ground what?
The input?
Okay, so if I ground the input, or really, to draw it more correctly here, grounding the input would kind of mean, you know, short these 2 ports out. What would that tell me? Which of these 2 noise sources would it tell me about?
VN.
Current noise.
I heard actually both possible answers, so now we just got to figure out which one is right. So who thinks it's going to tell you about the noise current? Noise voltage? Okay, so I agree with the noise voltage guys, although I suppose if you said current, you know, it kind of depends on what you were thinking of doing the measurement. So if I short this thing out, what's going to happen is all of that noise current is going to flow through that short, right? In other words, none of it's going to go into the input impedance of the amplifier. That means that if I looked at the output over here, I basically have no effect on the output in terms of the current noise, right? Because none of that current noise flowed into the amplifier. That means that if I measured the output, what I actually would be measuring is the voltage noise. Right? Because the voltage noise would just show up at that input port right there and cause the amplifier's output to be noisy. Okay? So if I want to measure the voltage noise, I short out the input. Okay, so now obviously, what if I want to measure the current noise? Then what do I do? Yeah, you open circuit the input, right? Because if you open circuit the input, you know, floating batteries do nothing because they're just floating. All of this current would flow into the input impedance of the amplifier, and if I measured the output, that would tell me the input referred current noise density. Okay? And so in fact, that's exactly what this next slide here over here says. It just says if you have some noisy 2-port and you want to figure out what's the sort of equivalent noise that it's generating, either you short or you open the input and then measure what happens at the output, and it tells you those 2 quantities. Okay? Now, I've kind of spent a little bit of time talking about, you know, noise current versus noise voltage, because this actually gives you a little bit of intuition as to why you want to build certain amplifiers in certain ways. Okay? So, as an example, as we just said, right, if I open circuited the input, then it would be all about current noise. That would set everything, right? Whereas if I short-circuited the input, it'd be all about voltage noise. Well, a lot of times, particularly if you're talking about a sensor or something like that, or actually even a radio, you know very well what kind of impedance is going to be driving you, right? So if I know, as an example, that I'm going to be driven by a high impedance source, what I really want is an amplifier that has very, very low noise current, right? Because if it has big noise current, then actually I'm going to get a lot of noise out of this thing, right? On the other hand, if I'm going to be driven by a low impedance source, for example, like an antenna, which is 50 ohms, which is pretty low impedance, then what I really want is actually a very low noise voltage, right? Because even if there's a lot of noise current, it's just going to get shunted out by that low input impedance, right? So in fact, this is exactly why if you kind of look at, as an example, what's the best transistor for me to use for a radio versus what's the best transistor for me to use for, say, a capacitive sensor? Well, in the radio, where I have a low input impedance, BJTs rule, right? Because basically they have noise current at the input just because you're flowing through that base emitter junction. But because the GM per unit current is so high, they have a low noise voltage, right? So that's good news. On the other hand, if I had like a capacitive sensor, which means, if I say capacitive sensor, that should immediately sort of say something to you, oh, capacitive, like high impedance at DC, right? Well, high impedance at DC means, well, I really want an amplifier with very low noise current. And by the way, with a MOSFET, if you think about it, since I have no input impedance, or I should say the input impedance is infinite, that basically means the input referred noise current is also quote-unquote zero. That's not exactly true if you sort of look at really high frequencies, but ballpark, that's essentially the case. Okay? In fact, this even sort of touches on something more interesting than this, which is, let's say I wasn't somewhere in one of these two extremes. Let's say I wasn't at, something very low or very high. But I'm somewhere in the middle, and maybe I even actually have some freedom to play around with what that source impedance driving me is. Maybe I can build some transformation network or something like that. Well, turns out you can actually figure out what is the optimum source impedance that you want to be driven by, right? Because you can imagine as I tune this source impedance around, I'm going to be moving around between the contributions of these two noise sources, right? If I pick that just right, I should be able to balance it out so that the total noise I get at the output is minimized. And so indeed, if you do that, here I'm just sort of showing you what is the total output noise as a function of RS. I'm not going to walk through the math because it's not particularly interesting. But you could basically take the derivative of this whole thing and figure out what's the optimum RS to use. And as you might expect, you actually come up with something that intuitively makes a lot of sense. It basically tells you, okay, if I have a certain amplifier that has a certain voltage noise and a certain current noise, then basically the best source impedance to get driven by is something that essentially looks like the ratio between that voltage noise and that current noise. Okay? Because obviously that has the units of impedance, and it kind of makes sense. It's sort of balancing those two contributions out. Okay? So if you look at these expressions, all I did was just redefine some intermediate variables, the Rn and the Gn. Those are just like equivalent resistors that would give you the same amount of either noise, voltage or current noise densities. And again, if you sort of work it out, it tells you that the best impedance to be driven by is exactly that ratio of the voltage noise to the current noise. Okay, and again, it's really just all about balancing those two contributions out. Any kind of questions on this, or? Okay, so we'll pick back up with this on Thursday. See you guys then.